Good morning to everyone. I want to thank every one of you for being in this presentation. My name is Fabian Rada. It's a pleasure to be here today to talk about how we correlate SOM volumes generated with Paradise with discrete well-logged data using statistical tools. In this case, this is a question: what were the interpretation objectives and the geologic setting? The intention was to detect the lithological contrast of a reservoir and map the extension of the best neurons. It means the neurons that have the best petrophysical values for V-shale, effective porosity, and water saturation. The reservoir, in this case, is dolomized calcareous breccias that lays on the upper Cretaceous section, are carbonates, and the depth in the area of interest ranges between 3,000 and 4,000 meters below sea level. In this slide, I want to show you the general workflow that we commonly use. And the first box at the left implies the selection of several attributes that respond to the detection of or are useful for detect lithological contrast. They are common instantaneous attributes as attenuation, envelope, instantaneous frequency, Hilbert, the amplitude, relative acoustic impedance, the envelope second derivative, the sweetness, and thin bed. So all of these attributes respond to lithological contrast. We know this because we had done several tests and for the bibliography, no? Also we applied principal component analysis in this step in order to select the most contributed attributes in order of variance, and of course the knowledge about the use of attributes and the knowledge about the geological setting of the zone. So we run several SOMs, and the second step is to review the SOMs using vertical sections, sculpted volumes, or horizon probes, geobodies, stratal slicing, so we can see the patterns in the data, in the results, in the classifications, and select maybe a couple of volumes, of some volumes, so we can extract those volumes along the well path and see how these neuron numbers correspond to several properties, yes, and understand the behavior of those properties and and how they are distributed in the area. I mean, with the SOM volume classification. The next step is to prepare the data to do this calibration using bivariate and multivariate statistical analysis. It means contingency tables, chi-square test, and cluster analysis, and the review of the petrophysical properties. So at the end, we will have a calibrated SOM volume that could be ready for use. Yeah. In the second step, as I show you in the workflow, we review the self-organizing map or SOM results in vertical sections. And this is an example in this slide. You can see that in black you have the amplitude traces or wiggles. So you can see that the top of the reservoir is a peak, but with the SOM classification, the colorful type of data that you can see in this section, you can see more detail than you be able to see with this amplitude. So towards the top of the reservoir, this one, you can see the samples grouped by neuron 11 in this color yellow and ochre yellow. And in the first analysis were related with calcareous sandstone that overlies the fine calcareous breccia in this Cretaceous section or units that are the most productive, BK and BK1, and were grouped by neurons 1 and 2, the yellow and the pink that you can see in this section, yellow and pink. Okay, towards the base of BK2 unit, the facies are medium calcareous breccia, not fine as at the top. And in some places, the neuron number 23 and 24 is pink, kind of pink and blue, kind of pink, and in some places blue, stand out, and which being of such different numbering from those numbers identified in the upper sections or units of this reservoir. And these changes seems to be responding to possible differences in rock quality. And we have a question why we use the statistical tools with the machine learning results that came from Paradise. But, well, because we wanted to link the SOM results that are discrete values and compare with the well-logged data. So we think that the statistical tools are a good way to explain the relationship between the SOM volumes and well-logged data and how petrophysical properties were discretized by SOM results. This work that I'm presenting today is based in a methodology published in September edition in First Break magazine of the EAGE in 2019. And this article is available for you in Geophysical Insights webpage. So what process and tools we employed and what were the results? The first step was to build a 3D grid. In this grid, each cell must have the same dimensions as original seismic data, sampling interval and bin size, of course. And the second step is to assign the values of the SOM volume to this grid in order to visualize the vertical proportion curve of the SOM, this figure that I'm showing you. And the second objective is to create a discrete property that could be extracted along the wells, yeah, the well paths. So the third one is to apply the statistical analysis itself. So in a qualitative way, we based on the expertise of interpreters, trying to see patterns, or maybe I'm talking about not using statistics at the beginning. This is the common way. You see the number of the neurons along the well path and trying to match with the well log information, well logs, production data, cores, etc. So this is qualitative, and the interpreters could have a good level of expertise, and several times we are successful, yeah. But we were looking for a quantitative approach, and please let me show you in the next slides how we do this process. So in order to run a more detailed analysis, we export the logs, continuous and also the discrete logs, including the SOM classifications as last format, and the sample interval for well logs, including the SOM classification, is half a feet or 0.15 meters. So we export these last files with this information and prepare the data in order to be analyzed using an in-house development that we call cross-table and cross-table Petro in order to run the statistical analysis. So part of this statistical analysis is the chi-square independence test, and the chi-square test was created by Pearson more than 100 years ago, and this is frequently used in health and medicine or biology or social sciences. And in this slide, I will show you an example of a medical case, but the goal is to analyze the relationship between two qualitative variables. It means that the values of the variables are not numeric, are not scalars, they are categories, as occurs with the neurons of a SOM generated with Paradise. Okay, this is a medical example. As you can see, you have several medical or type of treatments, treatment 1, 2, 3, and 4, and you have 3 levels of responses obtained from the experiment. In this case, the patient responds in a worse way, or the same response, or a better response to the treatment, to the type of treatment. Okay, so in this contingency table, you have one variable in the columns and the other variables in the rows. So this is the observed frequencies of the experiment, the real observed frequencies. So you have to establish 2 hypotheses. The first is the null hypothesis that refers that the variables are independent, and the alternative hypothesis is that correspond to the dependency of the variables. So how these hypotheses are contrasted, or the null hypothesis is contrasted. So you have to the frequencies that would be expected to be obtained if the 2 variables were independent are calculated and compared with the observed frequencies. So you have to build a expected frequencies table, and this table is easy to construct. You only have to do these simple mathematical operations between the marginal frequencies in the columns by the rows and dividing by the total of samples. So you obtain the expected frequency for these cells. You have to obtain the expected frequency for the entire cells in the table. This is another example, another cell. So you have to multiply this value by this and divide it by the total, and so on. It's important to verify that in the table of expected frequencies, the percentage of cells with expected frequencies lower than 5 is less than 20% of the cells. A higher value will invalidate the chi-square test, and the statistical methodology allows to collapse or regroup contiguous categories or cells with expected values less than 5. Yeah. Continuing with this medical example of chi-square, we calculate the critical chi-square value with a confidence level of alpha and 6 degrees of freedom. So we compare the values, and the null hypothesis says if the calculated values is bigger than the critical value, so you have to reject the null hypothesis and accept the alternative hypothesis. So in this way, we demonstrate that the response to the treatment and the treatment are related. Yeah, the variables are dependent, in other words. So let me show you how we adapted this statistical tool to our geoscience world. So in this slide, I show you two contingency tables built from the count of net reservoir property by neuron. Yeah, at the left, we have the contingency table of lithological contrast SOM versus the net reservoir categories. Net reservoir has two categories. The first one, net reservoir itself, that has the capacity, the storage capacity, the porous space, and the no reservoir part of this. Yeah. So at the right, you have the expected frequencies. So you have maybe the count of neurons observed. For maybe neuron 1, you have 43 times the no reservoir category, and 3, 5, 7 the net reservoir. And maybe you have in the expected frequencies 55 and 345. Yeah, the values are closer. And of course, we are looking in this example for neurons that have good counts in net reservoir. Yeah, because they represent neurons that are the reservoir. So maybe neurons 1 and 2 are reservoir. Maybe the 3 no, because has null value here. Maybe the 5 is almost the same amount, so it may be a mixture of things. So you have to interpret these results and you know, find a geological sense of this evidence. Next, in this slide, I show you two contingency tables. At the left, we have the contingency table of this lithological contrast SOM. You can see in some slides the word MAO. MAO means self-organizing maps in Spanish. So these contingency tables represent the facies by neuron. So in this example, you have at the left the observed frequencies, and the best properties facies in this reservoir are medium and fine calcareous breccia. Yes. At the right, you have the expected frequencies. And again, if you look at the details, neuron number 1 have a lot of amount in or counts in fine calcareous breccia, the best facies in this field. Number two is pure fine calcareous breccia. Number three, medium, but you can see the frequencies also, the number of times that you count some properties by neuron. So you can say if, or think if maybe number three have lower frequencies, and maybe you have to investigate a little bit more in your data in order to have a criteria. It means that if makes sense to the geological significance in this area. Okay, another contingency table built from a continuous property, in this case porosity. The first thing that we have to do is to regroup this continuous variable, the porosity, into classes, in this case by ranges, and so you will be able to compare categorical values with neurons, yeah, discrete values. So in this case, we rearrange or regroup the porosity by those range: null, low, medium, or high porosity. Okay, and again, the neuron number one, maybe you have these counts null and low categories of porosity, but you have a little bit more proportions in medium and high categories of porosity. The same behavior occurs with the number two, and maybe you have the inverse or the opposite trend with the neuron 5. You have null, higher nulls and low counts. Sorry. Okay. This is an easier way to analyze the contingency tables, and I mean all those graphs that I'm showing you came from the contingency tables, and that you already see in the previous slides. So in this case, the proportion of each category for net reservoir, for facies, and for porosity regroup by ranges are shown, and it's easy to see the observed frequencies for neuron 1 in yellow, 2, 8, 11, 12, 16, 20, 22, and 24. Yeah, for net reservoir. And also you can see the same neurons have facies in fine and medium calcareous breccia. And in the chart in the bottom left corner, yeah, for medium and high values of porosity, the green and the yellow bars. We want to look more about the petrophysical properties behavior from the well logs, sorry, and how correspond to our SOM classification neurons. So you can see maybe the distribution of those petrophysical properties: effective porosity, water saturation, and V-clay. And you can see how some neurons maybe are reservoir and correspond to the net reservoir part, but maybe have higher or high values of water saturation. So you have to be careful, and this is the way we do to inspect the petrophysical values or evaluations against the SOM neurons. Okay, With the same data from contingency table for net reservoir in this case, and the SOM, we build a radar or spider charts. So you can see if the observed frequencies on the SOM neurons are scoring high or low within the net reservoir and no reservoir properties or categories. In this case, you can see the proportion. Of course, you have this kind of chart show you the magnitude, and you can see the neuron 1, 2, 3, 4, so on. And you can see in the table the number 1 has a big proportion of net reservoir, the number 2 also, and so on. Also, we might generate these same graphics, bars or radars, charts from the expected frequencies if the two variables were independent. And finally, we computed the experimental chi-square for this data, and it's bigger than, this is the experimental, and it's bigger than the theoretical chi-square value. So you have to reject the null hypothesis and accept the alternative, so the variables are dependent, or the sum for lithological contrast and the net reservoir property relates each other. Yeah. Also, we calculated the likelihood ratio and the p-value for the chi-square and p-value for likelihood ratio. With this significance level, these degrees of freedom, 17. We have I think English is the statistical power. This one, and we have two types of error type 1 and error type 2 of these chi-square distributions. So investigating with 3 different association indices like Kramer, the corrected contingency coefficient, and the Shupro coefficient, we have for this data a moderate relationship. Yeah. Okay, in contingency tables with nominal variables, once it has been established that there is a significant association between two variables using the chi-square or likelihood ratio statistics, and the association has been quantified with some index, the Haberman residuals constitute the best tool available until now to accurately interpret the meaning of the detected association. The different percentages that we see in this top right corner can help us to distinguish the possible association patterns, but it's the Haberman residuals that allow us to interpret the relation between the variables. So it is not enough to look at those z-scores values that are greater than, in absolute value, than 1.96. So values greater than this value indicates a larger relationship between the categories. Yeah, it means that the larger the absolute value of the residual, the larger contribution of this cell or this neuron to the magnitude of chi-square. So I mean that under the null hypothesis that the two variables are independent, the adjusted residuals will have a standard normal distribution. It means that with a mean of 0 and a standard deviation of 1. So the adjusted residual that is more than 1.96 indicates that the number of cases in that cell is significantly larger than would be expected if the null hypothesis were true. This is with a 95% of certainty. and an adjusted residual that is less than minus 1.96 indicates that the number of cases in that cell is significantly smaller than would be expected if the null hypothesis were true. In other words, cell-by-cell comparison of observed and estimated expected frequencies help us to better understand the nature of the evidence. And cells with large residuals show a greater discrepancy than we would expect if the variables were truly independent. So there are several neurons that the magnitude of the Habermas residuals is too long, so something is going on with these cells or neurons. Yeah. This kind of graphics, the Habermas residuals or the percentage of the absolute values, Habermas residuals, the percentages, and the observed frequencies can be generated as spider or radar charts. And as the SOM classification is for lithological contrast, it means the attributes selected respond to lithological contrast. We checked the count of net reservoir and no reservoir by each neuron. So you can see the color map. You can see neuron 1, the 2, 3, 4, and the net reservoir is the bar at the right, and the no reservoir proportions at the left. Neuron number 1, 2, 3, etc. So you can see that some neurons have predominance of net reservoir, like number 1 or 2, but maybe this neuron is the opposite. Or some neurons have similar counts. Yeah, this is a way to observe the behavior of this property. Sorry. Also, you can see the porosity histograms by neuron. Neuron number 1, neuron number 2, neuron 3, and so on. And you can see the distributions of, in this case, porosity by neuron, and get more information from the data. Yeah, the same occur with V-shale. In this carbonate reservoir, you have this vertical dotted line that represents the cutoff value. So you can see that in almost all the neurons, you have distributions below this cutoff value, and is at least in Mexico, this is the behavior. Yeah. Finally, we review water saturation distribution by each neuron to get a different perspective of the data, because at the end of the day, we want to find hydrocarbons, no? So in water saturation, you have the vertical dotted red line that represent the cutoff value, and you can see that several neurons are okay, but maybe others are mixed or are, as I'm indicating with the laser point, distribution with high values of water saturations. So you have to be careful, or we have to be careful, in order to say if those neurons are really representing the good part of the reservoir. Another way to see the behavior of the data is through cross plots. Of course, in this case, we have porosity versus V-shale. for each neuron, neuron number 1, neuron number 2, neuron number 3, and so on. All the neurons that were connected or extracted along the well paths in the reservoir or in the reservoir, within the reservoir. Sorry. So you can see another cross plots. In this case, water saturation and V shale versus V shale by neuron. Water saturation versus porosity. But you can build the graphs, cross plots, box plots, bar charts, spider charts, using another properties, maybe Poisson or VPVS ratio or acoustic impedance and so on. Yeah. Okay. In this slide is very interesting graph because it's another way to analyze the behavior of the neurons through the percentiles of the petrophysical values. In this case, the first one is V shale, and you have this black horizontal dotted line that represents the cutoff value. As you can see, this is the legend for the neurons. Not only the neurons, be aware of the frequencies or the number of times that each neuron has this property, V shale. So maybe you have 400 for number 1 or almost 200 for the number 2, but the number 3 only has 5 samples. So this is a way to make a further analysis and apply the criteria in a good way. So maybe the number in V shale, as you can see, most of the neurons has the maybe percentile 70 are with or represents V shale volumes lower than the cutoff values, but maybe this one have this portion from the percentile 75, you have some data above the cutoff value, so you have to be careful with this neuron. This is the number, help me, the number 17. You have only 20 times this property. Okay, the porosity, again, the dotted horizontal line is the cutoff value for porosity. And in this reservoir, few neurons are anomalous, yeah. Water saturation, you can see neuron number 1, the yellow, and 2, this pink with a little dot or circle, are very, very low values of water saturation. But maybe you have another neurons that have another trends, so you have to be careful. So using the radar charts, we can see the same properties, and this is another tool to analyze the behavior of the petrophysical values or properties by neuron. Neuron number 1, 2, 3, 5, and so on. For some interpreters, radar charts are an easier way than histograms to analyze the data. Yeah, but of course they represent in a different way the same pattern. Okay. As we have been seen so far, we use different graphics for analysis like bars, radar charts, histograms, among others, that are useful to understand the behavior of the neurons as a function of the petrophysical values from well-logged data. Additionally, we wanted to apply a tool from multivariate statistics known as cluster analysis that allows us to identify the neurons with higher relation or similar characteristics. In this case, from two properties, petrophysical properties, porosity and volume of shale. And they are conformed by the cluster number 1 and the cluster number 2. The number 1 is remarked in blue, and the remarked in blue at the top of this table have the lowest values of B shale, are very clean, and porosity values ranging between 4 and 17%. The cluster number 2, the neurons in red, have larger values of V clay with respect to cluster 1, and have porosity values ranging between 0 and 8%. So it's very important to note that the frequency of the points for each neuron, as we saw in the previous slides. So we have to be aware of neurons with low counts of samples. It means in this case number 9, 23, 21, 13, and 17. And we must identify if those neurons have geological meaning or not. We ran a second cluster analysis, but this was conducted using 3 petrophysical properties. They are V shale, porosity, and water saturation. And we found 6 different groups. The cluster number 2 with neuron 1 and 8, that is in this place, and the cluster number 4, neurons 2 and 20 and 2, are the neurons that have very clean values of V shale, good porosity values, almost 10%, and saturation values of almost 30, or in this case 15 or to 18. Yeah, they are another neurons that are separated in separated cluster and represents bad portion of the reservoir. So with this technique, we figure out how the petrophysical values correspond to the classified volume. But we, in our methodology, we don't only use the statistical analysis. Also, we use different visualization techniques as plan views, vertical sections, 3D perspective views, vertical proportion curves, cross plots, box plots, radar plots, among others. And it's very important the geological knowledge in the area of interest, in order to understand a little bit more the reservoirs that we are studying. As a conclusion, well, for property prediction, we analyze the SOM classification volumes along the the well path, and against the well log data using statistical and geostatistical tools, and it was possible to perform the calibration and better understanding of the SOM classification. In this case, the lithological contrast detection is an example, and in this case, we demonstrated that respond to the reservoir, facies, and porosity regrouped by ranges. As I said, other properties from well logs could be treated as explanatory variables. It means maybe net pay, VP/VH ratio, Poisson, among others. And also other SOMs volumes could be treated as response variables, like maybe a SOM classification using attributes that only responds to pay volume or fluids, or maybe porosity or fractures, among others. And finally, I would like to thanks to Hal Green for this opportunity, for inviting us to present, and his constant support. Also to Ivan Marroquin for fruitful technical sessions, and Tom Smith from Geophysical Insights for their contributing comments and suggestions. Also thanks to Laura Curil from Alberta for her support, and my gratitude to my colleagues David, Marco, and Cesar for their constant effort daily. And finally, I would like to express my public gratitude to Reynaldo for his help in this process of continual learning. I think we got to the end of this presentation, and